So this is where we finally get into calculus. First we'll build this idea, 3.2 limits of visual approach. For each graph, consider is there a limit. So this is just intuitive here. Recent social trends in Canada. Look at this. Live births per 1,000 Canadian females, age 20 through 24. So early 20s. Look back in the day, 1960. Okay, that makes sense. A lot from what you guys know, 50-some, 60-some years ago, women tended to have children earlier in their lives, right? And they're also, I think, it wouldn't be a surprise that there was more births, or like more children per couple, too, right? All kinds of reasons. What is a major reason you guys think of? How has society changed a lot now in the year 2000? Like that's where this graph ends, the 2000s. Today. What's the big difference from 1960s to the nowadays?
Better birth control.
Birth control, period. Two, socially acceptable. Okay, but why was there the sexual revolution, they call it, because of birth control and stuff like this in the 60s? What did that lead to, without me saying? Well, how many of you have, we use the phrase stay-at-home mother. How many of you have a parent that stays at home and does the housekeeping, the women's work? Yeah, currently you do? Okay. Was that more common, more prevalent, do you think? From what you know, you didn't live then in the 60s? Yes. Careers now too, right? Anything boys can do, girls can do better, you know, that kind of stuff. Except become the President of the United States, apparently. That poor lady. I didn't realize the American people hated the pantsuit so much. I actually think it was a fashion thing. Anyways. Is there a trend here? Okay. If I just do a loose, like, okay, my finger got off because I couldn't see under my arm the shadow. Anyways. But you get the idea, right? Does this seem to be settling on a value over time? So, as we approach, okay, I could say as x approaches infinity, as it goes on and on and on, does it look like we're settling on a value here? Kind of, eh? It might still be going lower though, eh?
Yeah.
Is there a value you can't go lower than that makes sense in this? Live births per 1,000? Zero. No births, yeah. You'd never have this graph go so low at zero. You might have a time when, per 1,000 females, there's only 10 births, and that would look like, you know, that'd be really low on that chart, right? Because I got that counted in 10. But right now, there's conceivably a limit. Like this could settle on a value. Not sure. But it appears if you were to predict the year 2020, and we could wait another few years and get the data, what would you guys predict the value would be? I know it's a guesstimate, but what would you predict? Or what did I have a question underneath here? Is the year 2020? Okay, 2005. What do you think the birth rate is for 2005? I forgot that I had the questions printed here. Give me a guesstimate. No, it does seem to be going down though. So maybe the next diamond would be on 50. That'd be a good group. And if I went backwards to the 55s, look at this end here. It's kind of interesting. Now this is only based on 2 dots. What do you think in 1955 though?
Maybe not quite.
If you're just basing it on this, it looks like maybe it would have been a little higher, but probably not dramatically different, right? And you hear maybe stories now, your grandparents are a generation different than my grandparents. My grandparents' generation. And even my mom and dad, they were just starting to get out of that. You'd hear families of 10 children, 12 children, etc. My mom has 6 siblings, and those were the ones that survived. Like, obviously healthcare was different then too. So, it might have been a lot higher then too. Okay, so jot in your estimates there. Now, we haven't really done calculus, but this is this idea here. How about this? And I purposefully stopped the data here. 1990s-ish, okay? Based on this graph here for the 100-meter record time versus the year. Okay, way back when, 10.6 seconds. Good luck trying to beat that here. But that was the world record, 100 years ago-ish. Then there's a big jump here, right? 10.4 seconds. Is that really a big jump? No, I've only expanded the graph. This is from 10.6 seconds down to 9.8. That isn't even a full second of data. We're talking, when you're talking Olympics, you're talking very tiny amounts. So always pay attention to a scale, because this looks like a dramatic change, but we're talking decimal seconds, right? Anyways, always look at your axes and see what they're actually measured in. Because somebody will say, look at this time, it was cut in half by the year 1935 or something like that. It wasn't cut in half though, right? Because this is 10.6, that'd be 5 seconds if you cut. Anyways, this kind of looks like the trend, doesn't it? So, using this graph only, if you were to predict a record to be in 2000, now we know this and I use this, what would you predict in 2000 and 2013? You guys just throw some out there.
I would say it's still like maybe around 9.9.
9.9-ish, you guys think? Does that sound, that's what this data suggests, right? And market analysts like economics, they use predictions like this based on the best available data, right? You don't know what the heck's going to happen. All I know for sure is that the record can't go up, right? It's no longer a record. Does this make sense, too? 100-meter dash, that there is going to be there's a time, and we don't know what it is, but you can't have it go down to 0. Of course, 0 would be the quickest. You can't do that. There's going to be a value that we get a limit on, right? Now, what's the big difference between 100 years ago and now? What do you think? Health is a huge thing. Also, the kind of runners you guys, like even just skates that you guys have, if you skate. I have an old pair of skates that are 20 years old or whatever, but now this 30 years ago and stuff, when I was a kid, I'm 42, when I was a kid, skates that we had, you guys would laugh if I went to a hockey rink with my old skates from when I was 4 years old and stuff like this. They look like ancient machines. The technology is better. People train better. Now countries actually pay athletes to train and stuff like this. Who knows, maybe the doping techniques are way better too. I'm cynical there, but I mean, there's stuff that people take that isn't detected. So with this data, you'd probably not predict something much further off of 9.8, like 9.9-ish, maybe just a smidgen under, right?
Yeah.
Now, we'll come back to that after. Men's life expectancy versus year of birth. Once again, look at the axis. I'm going from 58 to 83. Meaning, my grandparents' ages, my grandparents were 1907 and stuff like this. They're not on the chart. But you guys might have grandparents that were born in the 30s or 40s, I don't know, maybe 20s and stuff like this. If you were born in the 20s, your life expectancy, 58. Now, you guys were all born just before the year 2000, I think. But here we can use this as a, you guys are roughly 77-ish. What do you think the big difference was here? 58. This is an average, right? Life expectancy. Do you think most people died around 58? Half of them did, the age?
No.
Childbirth, I'm saying this out. Now, if you average in a bunch of zeros, people who didn't make it past their first year or two as well, which happened because healthcare wasn't as good. You average in a bunch of zeros with a bunch of 70s-year-olds and stuff like this, right? That's where you get lower averages. Once you made it out of childhood, your life expectancy wasn't too different. It was still lower than today, but low. I think that was only men. Eh? Now, would we think, okay, it looked like, just suggested on here, if I drew a smooth curve. Sky's the limit? Does this make sense?
No.
There's gonna be a leveling off sometime. I don't know when. But we've got more centurions living today than ever before. What do you call that? Pension system and stuff like this. Old age security, it actually didn't change CPP. The age at which you're eligible to get it, I think that's changed. I'm not so far off for me, I'm not too worried. It's 25 years from now. I think it's 67 or 68. Because when they designed this stuff 40 years ago, people, if you'd retire at 65, you probably weren't on the payroll on average much more than 7 or 8 years. Now people are living into their 90s. It's quite common. Life expectancy has gone up into close to the 80s for women especially. So that same plan that was set up to pay out a person for an extra 7 or 8 years of their life, from 60, on average to 70 something, is now paying out people closer to 80, so it's getting an extra 10 years out of that same system. That's why it was looked at, and we had to, I don't know if you guys even paid attention to that, but there was a change in when you're eligible to get some of these programs, and it's probably a smart one. People are living longer. What would you predict the life expectancy is for a man born in 2020 then, at the end of the graph, and born in 1948? Well, 1948 we could be pretty confident because it's in between these two values, eh? Let's do the 1948. What do you guys guess there? 65, which is pretty reasonable, eh? That's more accurate. That's interpolated in between data. Now, 2020, it looks to be growing pretty much, doesn't it?
I would say like around 80.
Yeah, 83 wouldn't be a long shot, eh? 82, 83, something like that. It doesn't seem to have reached the limit, does it? I don't think so. Sky's not the limit, though, but yeah.
Well, unless we go to Mars.
Who knows?
Yeah.
Who knows? Now, this is the same data I have, except I've added in data after 1990. Remember our graph from before? And it appeared, and this is to show you that models of predictions and stuff like this, weather patterns and stuff, are always only as good as the data you're giving it, right? Now, before we said the data, all the data suggested that we would not be much underneath 9.9, maybe in the 9.8s, right?
Yeah.
Except sometimes, Usain Bolt in this case, bang. So what does this tell us? Mathematical models are good things, and we got to use them to make predictions and stuff like this. Like I said, weather, financial predictions, markets, and stuff like that. Science, we use them to predict all kinds of systems and stuff like that, engineering and stuff like this. When will something fail, like pulling stuff up? But sometimes you'll get something misled. After keeping data for 100 years, it's actually quite rare now that you get somebody who is so far off the norm. Usain Bolt is. He just, all of a sudden, like you can just see the data and then bang, a dramatic shift, right? So that happens. Just to be aware you're using mathematical models. Economic concepts, markets and stuff like this, Dow Jones, TSX, you hear this stuff. Investments, currency, those things are so erratic. They do have models to predict, but the further you predict into the future, the tougher it is. Because all of a sudden there'll be just something that seems to be going smooth, and then bang, something goes way up, or else a crash, a market crash, and values go down in economics. So, I still think there's a limit to this race, but I think so. But is it easy to predict? No, but it can't get, like we said, you can't go 0 seconds. You know it has to be something probably greater than 5. I'm willing to put, not willing to put because I don't have the money to lose. But I would put money on in the next 20 years that it's not going to, like 5 is a very safe bet. It's not going to go underneath 5, I would think. Because we're still talking 9 seconds. I don't think it'll go under 9 seconds. Just, but I'm not studying this, and you know, like I said, if they get better drugs and stuff for doping, who knows? You guys getting the idea of limits there? This is just, we're using the word the common way, limits. Well, what about limits here? Well, like I said, this is the first step into it, and I'm just using this as just getting the idea kind of chapter, or section. This is the first concept we're going to learn about in calculus. Okay, so far you guys haven't done any calculus. More about limits. In mathematics, when you do this operation called the limit. Now, operations are things like multiplying, dividing, square roots. If I say you're taking the limit, it actually, one important thing about this is it allows you to get around the problem of dividing by 0. That's for a specific type of limit. We're going to call it the derivative later on. But let's take a look at this one here. This isn't the derivative, but it's an important limit. We can't evaluate this function, can we, at 0? Why? Because you're dividing by 0. What if you ask, what the heck would that be if you could divide by 0? Well, what we say is we sneak up on the left, we sneak up on the right, and we see what the limit, what is it looking like it would be. Okay, we can't actually put 0 into this. So I'm doing this data here when we have an indeterminate expression. Now, have you guys, I don't think you've ever used the word indeterminate. Right? What does it mean? It means 0. Oh, I can't do that there. Indeterminate means 0 out of 0. And I have that in words. An expression that gives 0 denominator and numerator at a given domain or x value. Okay? We can try to evaluate a limit though. Now you guys have done this before. Remember when you had a factored thing? So if I had something factored like this, x plus 2, x minus 3 over x plus 2. You guys have done this without calling anything to do with the calculus. You just said, well, if I take out the expression, out of the expression the common factor top and bottom, I can plug -2 into that expression, right? And it would give me -5 in that case. So you've kind of gotten around that problem of zeros, yet you know you have to leave a hole in the graph because the original expression had this. That's indeterminate, by the way. We can put -2 into there. This one, though, you can't factor a sine function. You can apply some things and stuff like this. But what if you did it this way? If I sneak up to 0, so I go x values 1 down to 0.01, 0.001 if you wish. But I think you can already see a pattern emerging here. If I plug in 1, by the way, I'm going to operate in radians, not degrees. Now, you guys don't have to do it. I've done the calculations are done for you. Okay. If I plug in 1, it's decimal 84. Plug in decimal 9, 0.87. Okay, you can see what's happening. Decimal 9, 94, 958, 8, 5, 9, 7, 9, 8. What do you guys just see this here? What does it look like it's approaching here underneath the box here? Take a wild guess. Yeah, 1. It does look that way. And, ooh, isn't this kind of weird, eh? It's like a magic box. Anyways, okay. It looks to be 0.99, 0.998, 0.99998. Okay, and why would I would stop going with 0.001? Why would I? It looks very close to 1. That is coming from the positive side, or the right-hand side of 0 on the number line. Okay, so if we approach it from the right, that's what I said here, approaching from the right. How do I notate that? I say I take the limit, and then you see x arrow 0 with a little plus sign. That means from the right on the number line. Now you might want to bring attention to that in your notes. just because that's new notation for you there. Okay, and you can just put in, eventually it ends up as 0.998. Okay. Boom. I'll just move that over. So if you were to plug in x values on the other one and find the values of f of x, but this is where x is approaching 0, but from the negative side, from the left on the x number line. Value slightly larger. I have a typo, don't I? I just copied and pasted there. Is that the way you guys, I noticed, yeah, silly old me.
From the left side,
Yep.
slightly smaller.
Oh gosh, anyways, unlock here. Whatever, you guys will just do it. When did I make that? So, left, smaller. There ye go. I'll just say something in here too. 3.2, and then we'll stop there. Page 3, error. Left. I'll correct it later on. Okay. You guys get the idea, though. It looks like actually the same values, doesn't it? And it is. Look at this magic, eh? Anyways. So we can say be pretty confident after looking at this list of values that if x approaches 0, you can't plug in 0, but if it approaches 0, it seems to be getting closer and closer to 1. That's what I have written down. Right? So, therefore, we can assume the limit as x gets closer and closer to 0 for sine of x over x. Fill in your answer. I think you know. Probably is 1. And guess what? I have this up on a sign here. You can see that one there? I have theta instead of x. It's 1. It's something we've used before. Now, I'm thinking you guys have the idea there. And I'm not going to say this is homework or anything like this, but I'll just finish up this last idea. It's not heavy stuff. It's not on the test at all. In order for a limit to exist, though, you got to approach it from the left and the right and get the same value both times. Now, evaluate. Now, the first one I have is the limit at -1. That means from the left and the right. So here's my -1, right?
Yeah.
Okay. Don't worry about the right hand side of the graph. If I came from the left, what does it look like, and what does it look like if I came from the right? Is it approaching the same value? You're darn tootin' it is, right? It looks like it's 0. You can actually just read it from the graph. In this case, it happens to be the same value that the actual function is at that point. Okay, that works. Even if this function, this is probably why I had an alternate value and I had a hole in here, still from the left and the right, it appears to be hitting 0, doesn't it? I'm going to erase that because there isn't a hole. Oh, undoodly-doo. There. Now, how about 2? I think you can see from left and right that you got 2 different values. From the left, the value approaches. From the right, the value approaches. I got to consider both. And how do I notate from the left? I'd say from the left, limit x approaching 2 with a minus sign like an exponent behind it of the function in the picture above. So you go to 2 on the x-axis, and from the left, so these values, if you approach this from the left, what does it look like it's giving you? 1. 1 for the y. From the right, same idea. I'd notate that limit of x approaching 2 from the right, that appears to be giving me a 3, doesn't it?
Yeah.
2 people are nodding in approval. If you guys have a question, please ask.
A limit is just like where it,
Seems to be ending up, whether it is there or not, it's where it looks like it would on the graph, right? And I just got to point that out. The actual function is only defined at what, 2.5ish, right? To have a dot there. And you don't get that answer for either the left or the right limit. Sometimes you do. So does the limit of x approaching 2 from either side have an answer? No answer, right? This is, we'd say, undefined here. Because the left and the right side don't give me the same thing. And lastly, I've got the picture, and I have the equation. I have both here. What about 0? Now this is 0 from either side, isn't it? From the left, from the right, it's a match. But that's not an actual value, but we could say better than undefined if you can. That seems to be going to negative infinity. So if you can be more specific than undefined, undefined doesn't tell you as much of as if I say it just goes down forever without bound, without end.
yeah.
Now what about B? X approaching 3. Well, from the left, it's negative infinity. From the right, it seems to be going up forever, positive infinity. That's not a match, so I can't just say it seems to be going up forever. So I'm going to just say undefined for that one, because it is a mismatch. Now this is different. X is approaching infinity. What does that look like with Hashim not blurting out the answer? What does that mean if the x is approaching infinity on the graph? Which is the x-axis?
Yeah.
The left-right axis, yeah. So if my numbers, like this is 3, this is 4, this is 5, as you go on forever to the right, what does it look like that graph is doing? Getting closer and closer to?
Here.
Yeah, it's coming, seems to be sitting as an asymptote on 0. Doesn't it seem to be the same thing on this side? Now, my drawing went a little goofy there. Even though it's coming from underneath on the negative side, it still seems to be going on the left side, out. If you chase that to infinity, it looks like the trend is to still hit 0, right? So there you go. Now, as far as these assignment questions and stuff like this, do yourself a favor and look over your stuff for the quiz tomorrow. Okay? Now,